Yeah, Brian just mentioned in the previous talk that the POP COE is using various tools, also Scorpy and friends. So you suspect you have a bottleneck, or you know you have a bottleneck because you did an assessment with the POP COE. So what do you do with it? What can you do about it? What do you want to, or how do you want to resolve it and make sure that this doesn't happen again in the future? So the best thing is go with Scorpy and friends. So what is this Scorpy all about? Scorpy is an infrastructure to instrument HPC applications and to perform performance measurements. It's open source. It's portable to all major HPC platforms, as Brian just mentioned. So we try to make it work on every platform we can get our hands on. It has proven scalability. Brian just showed an example where it scaled up to 300,000 cores. We have done successful measurements on our previous Blue Gene system up to 1.8 million parallel threads. So it's proven to be scalable. And it has a very active and community-driven development, which is supported by multiple partners. And in particular, we also maintain EasyBuild recipes, of course, but also, yeah, the other thing, and Fedora and OpenHPC packages as well. So these are really maintained by us, so we know what we're doing, which components we need to make things work. Instrumented applications can be used to produce different types of results. So you can generate call path profiles, or as we call them, runtime summaries, or detailed event traces, where you collect every single instance of some event happening, collect all the data in memory, in a memory buffer, and then flush it to disk at the end so that you can look at all the nifty details. So the basic idea is that we instrument the code once and can collect multiple different measurements with different configuration settings, and they are all chosen via environment variables. So basically the instrumentation is a one-off process in many cases. It's not always true, so sometimes you have to fiddle around with these things until you have a reasonable configuration found, but then you're free to do many different measurements, for example, at different scales or with different input data. That's the core of Scorpy, but there is actually a whole ecosystem of tools around it. So this is the 30,000 feet view on the ecosystem. At the bottom, you have the application where your Scorpy measurement system is baked in, which can collect via instrumentation wrappers data from all sorts of parallelism. So we support the usual ones, MPI, SHMEM, OpenMP, pthreads for process and thread level parallelism, all the accelerator-based APIs, CUDA, HIP, OpenACC, OpenCL. In the next release coming out, hopefully this month, also OpenMP target offloading, Cocos. We can record I/O activities and so forth. And we can also work together with the compiler to instrument your source code on the function level. And you can also add a user API to mark your own regions that are not captured by this. All of those goes into the Scorpy measurement infrastructure, which basically collects all these events, augments them with a timestamp, with hardware counter information optionally, and stores this data either in event traces or in call path profiles. These are kind of standardized in this ecosystem, and there is a whole bunch of tools sitting on top of these standardized file formats. So we have two tools, Vampire and the Scalasca Trace Tools, based on event traces, and we have 3.5 tools, Cube, XtraP, and Tau, with its database sitting on top of the call path profiles. And these are all complementary. So they have different strengths and weaknesses and focus on different aspects. So the nice thing is you do one measurement, or a few measurements, and you can then use multiple different analysis tools to look at different aspects of performance. Here in Jülich, we are involved in a bunch of these parts. So in the SCORP measurement core, the data formats, obviously, the Scalasca Trace Tools, and the Cube graphical user interface. That's what we are working on. The other tools are contributed by partners working together with just a brief recap what these tools are about. Vampire is an interactive trace data visualization and analysis tool. That's a commercial one. All the others are open source. Scalasca Trace Tools, that I will talk about in a second, focuses on automatic event trace analysis. Cube is an interactive report explorer to look at the profiles generated. Extra P supports empirical performance modeling, so it can automatically generate performance models out of a set of experiments. And Tau also provides a viewer, an interactive performance report viewer, and with its database also a possibility to do more advanced data mining, cross-experiment analysis. But they also provide additional instrumentation and measurement capabilities using SCORP as a data collection and storage backend. So now let's have a closer look at Scalasca. So that's my baby. Scalasca is a trace-based performance analysis toolset, so we operate on event traces. It's again open source and portable, the same platforms that SCORP supports, and also has proven its scalability. The main features are an automatic search for inefficiencies in this huge amount of, or potentially huge amount of trace data, in particular for wait states that occur. We identify the delays as root causes of these wait states and can identify the critical path profile, which can show you parallelization opportunities. The current focus is on MPI and the host side of OpenMP, POSIX thread to a limited extent, but the analysis of accelerator device activities is currently not supported. If you don't collect them, you can still use Scalasca to look at all the host side parts, which can still give you very valuable information, for example, on your MPI communication behavior. You need to interpret the results with a little bit of care, but that should be fairly straightforward, I'd say. So what does the Scalasca trace analysis do? Here's a simple example. You have some computation, some communication. In the first step, we will identify wait states. So in this case, so-called late sender situations, 2 of them, where a blocking receive is waiting for the corresponding send to start. So there, the process just sits idle and is waiting. Once we've done that, we classify these wait states into direct and indirect wait states, where indirect wait states are caused by other wait states. Direct ones are caused by some computation imbalance. Then we identify the delays causing these wait states. So in this case, we have an excess communication in the receive and an excess computation in the foo. And then we map or attribute these wait states that we've identified as delay costs onto these delays. So what are the costs caused by these delays? So the direct wait state on C is mapped onto the excess communication on B. And both the direct and wait state on B and the indirect one on C is mapped onto the excess computation on foo. And in addition, we can calculate the critical path profile by traversing the trace from back to front. Now, here's an example how this looks like in practice. With the Community Earth System model sea ice module, this experiment was done quite some time ago, but anyway, it nicely shows the advantage of this kind of analysis. So on the left-hand side, you have the different metrics. In the middle column, you have the call tree of the application. On the right-hand side, you have the individual processes, and if there were threads, you would see them. The analysis found a late sender weight state in an MPI weight, all in the ice boundary halo optic. And on the right-hand side, we can see the distribution across the system and ranks. Well, this was done at 4,000 MPI processes. And as you can imagine, a list with 4,000 numbers is hard to analyze. So we augmented the source code a little bit to capture the virtual topology of the application. So it has a 2D domain decomposition. And we captured that mapping onto the MPI ranks. And so we can nicely visualize how this data looks like. As you can see, these MPI weight states mostly occur in the equator region. So the further you get away from the ice, the more weight states you have, which is kind of obvious, but we could dig deeper. So we could identify the direct late sender weight states, and these are actually mostly on the border of the ice, of the sea ice, which makes sense, yeah? So you calculate sea ice, the next direct weight state is caused directly at the border. The indirect ones, okay, they are further away, so they propagate because these ranks in the middle, they are waiting for the others to finish their computation. However, when we look at the delay costs, so where do these weight states come from, they are not necessarily caused by the ranks processing the ice. So that was an interesting result that was really surprising us and also the developers of the code, that the late sender delay analysis identified a region here, what is it? Yeah, a little bit north of Japan or something, where we had, or where basically an imbalance was causing late sender weight states all across the system that was propagating along. And as far as I remember, the developers took a closer look and figured out that the solver was doing some extra iterations because some exit condition wasn't fully correct. So they could basically fix the solver. And this was really a tiny imbalance there that was causing a whole lot of weight states later on through all this propagation, and it was building up over many, many hops. Yeah, so that brings me to the end of my presentation, and I hope this could convince you that using tools can be very helpful in identifying bottlenecks and then give you a sense of where to modify your code, which portions you have to adapt. Thank you.
Thank you, Markus. Any questions? Can you go back to your example? The fact that we see the world map, is that pushed in, or is that just a result of how the partitioning happens?
The world map is basically due to the partitioning. Okay. So the world, or the domain decomposition, is really a 2D decomposition of the world in this particular code. Yeah. Okay. I think in a later revision, they changed it from 2D, or they had a different mapping, being more fine-grained and using some Hilbert curve distribution.
Destroys this whole visual aspect. Yeah. But maybe that raises the question or an idea. Could there be some kind of feature in, what is this, Cube, right?
Cube is the visualizer. Oh.
Well, yeah, in Cube, could there be some kind of feature in Cube where you could upload extra information about the problem itself, like this, let's say the semantics of the problem? I'm doing something across a world map that could help you, because I think part of the reason the developers realized what was going on has to do with where it happened, like physically on the map.
Right. So I mean, this is nicely visualizing where it happens, but you can, of course, also see this hotspot in the textual list. Yeah. And search for the maximum, basically. Yeah, but then, and then you know which rank it is.
Okay, but that's that's 2-3 steps to actually realize this is north of Japan. True. And that may be a factor. True. Small island, I don't know what.
In principle, you're right. There has been some work done in the past to actually map performance data onto application domains of various types. In this case, it's fairly simple. If you use MPI Cartesians, they are tracked automatically by SCORP. If you use graph topologies, things get crazy. Yeah, so this cube can only visualize Cartesian topologies.
Question from online. Does the tool also measure disk I/O?
Sorry, I didn't get that.
Does the tool also measure disk I/O? I/O. Yeah.
Disk I/O. So we capture POSIX I/O and MPI I/O, and that would end up in a separate metric up there. So we intercept the I/O calls at link time basically, and collect the number of bytes written and read. So that's the kind of information that you get there. There is no real weight state analysis for I/O yet. So for MPI, you could probably come up with something like that. For other types of I/O, you would need more information also from the file servers and combine that application level and system level data and so on.
Okay, thank you very much, Markus. And I will switch over to yet another speaker from Jülich Supercomputing Center, Alexander, but on a bit of a different topic. And it's a topic we must have on the agenda.